Hello and welcome to the DVCon 2021 presentation on early design and validation of an AI accelerator system-level performance using an HLS design methodology. My name is Michael Fingeroff and I'm a high-level synthesis technologist with Siemens EDA. In this presentation, we will discuss the challenges of designing AI ML hardware. We will provide an introduction to the MatchLib SystemC synthesis library. We will give an overview of convolutional neural networks, which is the design example we will be covering. And then we will perform early performance analysis of a CNN convolution, followed by architectural refinement for performance improvements, and we'll finish up with synthesis and RTL verification, along with some customer case studies. There are a number of challenges in designing AI ML hardware. The algorithmic complexity of today's algorithms and designs is growing faster than the ability of RTL designers to code and verify it in their design flow. Memory architectures are becoming increasingly complex. Efficient data movement is key for power, performance, and area. RTL verification costs continue to increase. Increased design complexity increases the number of bugs introduced during a hand-coded RTL design methodology. Furthermore, the cost of running RTL regressions involves server farms, electricity costs, licenses, and time. And lastly, slips in design schedules will kill total profits. Finding bugs during system integration is too late. Some research has shown that being 6 months late can lose up to 33% of lifetime profit for your design. We will now cover an introduction to the MatchLib SystemC library. MatchLib is a SystemC library of commonly used functions and components developed in partnership with NVIDIA. This consists of objects such as interfaces, FIFOs, and interconnects. MatchLib allows most design and verification of SoCs to be performed in SystemC. It allows verifying system-level performance earlier. It simulates up to 30x faster than RTL for timing-accurate simulation, and it easily plugs into existing digital verification flows. MatchLib enables control-oriented design with easy-to-use, throughput-accurate modeling and allows the designers to do more of the whole chip, including things such as DMA, arbiters, and bus interfaces. MatchLib and high-level synthesis enables an efficient verification flow. MatchLib involves the digital verification team at every stage of the design process. MatchLib models are smaller and faster. A SystemC model is typically about 1/10 or less the size of an equivalent RTL model. This means it is easier to verify and debug. MatchLib and SystemC allows designers to reuse the SystemC test bench to verify both the SystemC and the RTL. Catapult high-level synthesis makes it possible to automatically use the same test bench for SystemC and Verilog models. Placing a thin Verilog wrapper around the SystemC MatchLib design enables digital verification to start much earlier, even before any HLS has been run on the design. MatchLib reduces risk in modern digital design. Today's hardware designs often process huge sets of data with large intermediate results. This could be machine learning, computer vision, or 5G wireless. The hard part is often managing the data movement in the chip across all scenarios. The memory interconnect architecture often has more impact on the power and performance than the design of the computation units. Evaluating and verifying memory interconnect architecture at the RTL level is often not feasible. It is either too late in the design cycle, it requires too much work to evaluate multiple candidate architectures, and the most difficult and costly hardware and software problems are often found during system integration. If the integration is occurring first in an RTL design flow, it is very late and the problems will be very costly. MatchLib and SystemC HLS lets integration occur early when fixing problems is much cheaper. MatchLib Connections is a library and API of latency-insensitive channels. All of the components in the MatchLib library are synthesizable using high-level synthesis. The Connections library consists of ports and channels, and the ports implements a data-ready valid type protocol. Furthermore, MatchLib connections are templatized for any data type. The MatchLib push and pop function calls are synthesized to a data-ready valid protocol. When both valid and ready are high, a MatchLib transaction can complete. The example below demonstrates how to use the MatchLib Connections library in a SystemC design. The code on the left includes the MatchLib Connections library, defines a SystemC module, and then defines instances of connections interfaces for both inputs and outputs. This example has a single SC thread called main. The code on the right shows how MatchLib interfaces are reset in the reset action of the thread. And then within the body of the infinite while loop, the MatchLib input interface is read by calling the pop method, and the MatchLib output interface is written by calling the push method. MatchLib allows designers to simulate the pin-level behavior of the hardware before it has been synthesized. We call this the pre-HLS simulation. Post-HLS simulation is simulating the synthesized RTL that comes out of the HLS synthesis tool. The pre-HLS and post-HLS simulation throughputs will be almost identical. However, there can be differences in latency. Looking at the pre-HLS and post-HLS simulation shown below, we can see that the results are almost identical. MatchLib provides high-quality implementations of AXI4 master and slave interfaces. It is also possible to model custom bus interfaces using the base MatchLib library. The example on the right models a simple read bus interface with burst capability. The test bench that is used for this example also models a 2-cycle overhead for initiating a new burst. Looking at the code example on the right, it does signal reads to get address and burst size information from the top-level design interface, and then does a MatchLib push for both a read address channel and the read burst size. The do while loop then pops data off of the read data channel MatchLib interface and pushes the data out to a read data output channel. It continues to do this until the burst counter reaches 0. This simple example illustrates that small burst size or non-consecutive addresses can hurt performance by injecting dead cycles into the simulation. In this example, a burst is initiated by sending the address and burst size. The burst runs with a continuous throughput equal to 1 until the burst count finishes, and then there is a 2-cycle overhead before a new burst can be started. This is all demonstrated in the pre-HLS simulation. The next section provides a brief overview of convolutional neural networks. A convolutional neural network is an algorithm that is used to perform object classification and/or detection. Convolutional neural networks are made up of multiple layers, and most of the layers are convolutional layers. The majority of the computation is typically done in the convolutional layers and usually is responsible for over 99% of the computation. The majority of the memory traffic is also caused by the convolutional layers, and bias and activation functions are usually done in combination with the convolutional layers. The inputs into a convolutional layer are called feature maps, and the number of feature maps typically doubles from layer to layer. Because of this, pooling layers are used to reduce the feature map size in order to manage complexity. The fully connected layers are where classification is performed, and the softmax layer is used to normalize the outputs. For this tutorial, we will focus mostly on the convolutional layers. The CNN convolution algorithm is called COM2D. The COM2D algorithm has multiple input and output feature maps, and each of the output feature maps is a sum of separate convolutions across all of the input feature maps. So although the algorithm is very simple, it requires a massive amount of computation. The example here that illustrates the algorithm will not be ideal for a hardware implementation because of all the data movement that will be generated for the redundant reading of both the feature maps and the weights. There are a number of architectural challenges when implementing a CNN convolution in hardware. The memory architectures for the hardware need to leverage data reuse and parallelism. These architectures may have multiple processing engines or processing elements. This may include block-level parallelism as well as multi-block or module-level parallelism. The convolution engines will typically have many local small memories, as well as a complex interconnect in order to connect to some type of system bus, such as AXI4. The next section in this presentation will cover how we can perform early performance analysis of a CNN convolution using MatchLib. The design goals for this example is to implement a convolutional neural network for object detection and classification. This convolutional neural network will have 9 layers, and most of the convolutional layers will be performing a 3x3 convolution, which means that each 3x3 convolution requires 9 multiply accumulates. There are a total of 3.5 billion max per inference for this example, and the target hardware will be targeting a low power and performance Ring doorbell type application that needs to be able to perform 1 inference per second. And lastly, this design will run at a clock frequency of 500 megahertz. We begin with a direct conversion of the convolution algorithm to a high-level synthesis synthesizable bit-accurate implementation. In these examples, we will use a generic bus interface that was covered previously. However, it is also important to repeat that MatchLib supports a full complement of AXI4 bus masters and slaves. This example has the same loop nesting structure that was shown for the COM2D algorithm. It computes some indexes in order to read the data and the weights from memory. There is some zero padding done to deal with the image boundary. It computes a data index for the current feature map. It then pushes the address for the generic bus interface, and because all of the memory accesses are non-sequential in this algorithmic model, the burst size can only be set to 1. The weights are read in the same fashion as getting the feature map data. And lastly, it performs a multiply accumulate of the feature map data against the weights. The results of each multiply accumulate of a particular input feature map are summed up into an accumulation buffer, and when all input feature maps have been read for the current output, we copy the feature map data back to system memory. The copy back of the feature maps can sustain larger burst size. This synthesizable implementation, while functionally correct, contains no opportunity for parallelism. Running the SystemC MatchLib simulation took a very long time for this particular example, greater than 2 hours. And this was due to the large amount of context switching due to all of the non-sequential memory accesses on our generic bus interface. Furthermore, there were many redundant memory accesses because of the repeated rereading of both the data and the weights. The pre-HLS simulation showed that it took 14 seconds to simulate one inference. Our design goal is 1 second to perform one inference. So this design is not sufficient, and there is no need to go any further. The pre-HLS simulation has shown us everything we need to know in order to decide that the design should be optimized before we go to high-level synthesis. The next section covers how we can refine the architecture of our model to achieve our performance goals. When designing using high-level synthesis, the SystemC design must be architected for efficient data movement and reuse. This will not only improve simulation performance, but it will allow the high-level synthesis tool to extract parallelism. For a convolution in general, the most efficient hardware architecture will be some type of sliding window architecture, which will allow reuse of the feature map data. The sliding window architecture buffers up multiple lines of feature map data, which can then be fed into a set of parallel shift registers, allowing a parallel multiply accumulate to be performed for the convolution. The weights can be read once from system memory and stored in a set of on-chip registers for each input-output feature map combination. The results of the parallel multiply accumulate can be fed into a partial accumulation buffer, which will then write the data out for each output feature map. Our SystemC MatchLib design, shown on the right, has now been modified to perform a 9-weight burst for each input-output feature map combination. The weights are read and then stored in a register cache, which will allow them to be accessed in parallel. The feature maps are then burst a row at a time, where the burst size is set by the configuration parameter width. It should be mentioned that it is possible to burst an entire feature map in one go, but this would consume more of the bus bandwidth, locking out other bus transactions. Within the column loop, the feature map data is read one row at a time by calling the connections pop method, and that data is then fed into a sliding window architecture described in C++. The sliding window architecture then provides a window of data that can be accessed in parallel because the window of data is stored in registers. This will allow the KX and KY multiply accumulate loops to execute in one clock cycle because there is no dependence on the bus interface. The simulation results of our pre-HLS simulation of the convolution shows that the design goal has been met with a simulation time of 0.864 seconds. The pre-HLS simulation runtime was only 34 minutes to perform a single inference, and again, this requires performing 3.5 billion max. All of the other operations for the convolutional layers are assumed to run in software. This includes the bias, the activation function, and the max pooling. However, With our SystemC test bench, this has all been coded as pure untimed C++, which means it executes in 0 time. So assuming that our convolution engine needs to work in coordination with a CPU, the question that needs to be answered is what can MatchLib and SystemC tell us about the system level performance? The intended target hardware platform for this example is to have a system memory that is shared between the CPU, which performs the bias, activation, and max pulling functions, and the convolution accelerators. In this example, there is also no CPU cache. The SystemC test bench was rewritten to model the arbitrated memory between the CPU and our ML accelerator. The CPU instruction execution time was also approximated by adding delay into the SystemC test bench. After making these code changes, the pre-HLS simulation showed that the performance of the accelerator was being throttled by the CPU. This is because the accelerator has to wait while the CPU is executing the bias, activation, and max pulling functions. The pre-HLS simulation took approximately 2.6 seconds to perform a single inference, and the simulation runtime was approximately 63 minutes. For this example, the delays that were modeled in the test bench for the CPU were related to the time required to convert from a fixed point to floating point implementation. In order to improve the performance of our design and hit our design requirement of 1 inference per second, it is relatively simple to move the bias, activation, and max pulling functions into the accelerator. Furthermore, this costs very little in additional hardware when we finally synthesize the design. Adding these functions into the accelerator can be coded into the design where the feature map data is copied back to system memory. The code example on the right shows that we first get the bias from system memory for our generic bus interface. Then within the row copy loop, we set up the burst size for the current output feature map and push the output address and burst size to the generic memory output interface. The accumulation buffer is then read and the bias is added. And then the configuration parameter for the activation function is read, and if true, we perform the activation function. Likewise, if pulling is enabled, we perform max pulling using a similar sliding window architecture, and then push the data out to the generic bus interface. After these code modifications were made, the pre-HLS simulation now simulates in 0.9 seconds for a single inference, and the pre-HLS simulation runtime has been reduced to 30 minutes. This is because there is far less context switching now in our pre-HLS simulation. Looking at the waveforms for the pre-HLS simulation of our combined architecture shows that the memory bus is almost 100% utilized by our ML accelerator. This is because the input feature maps are reread from the system memory for each output feature map computation. The problem with this architecture then is that system memory accesses are an order of magnitude larger in terms of power consumption compared to on-chip buffering. In order to reduce memory traffic and power consumption, we need to add on-chip buffering into our design architecture. Buffering the feature maps on chip for this particular example will require approximately 800 kbytes for full buffering. The architecture is modified to split the design into two processes. There is a memory read process to access system memory via our generic bus interface. And then there is the convolution process, which includes the bias activation and pooling functions. The on-chip buffer is a shared instantiated SystemC memory that stores the feature maps between the processes. After adding the on-chip buffering, the pre-HLS simulation finishes in 0.93 seconds for a single inference, and the simulation runtime is now reduced to 20 minutes, again because of the reduction in context switching. Looking at the pre-HLS simulation waveforms, it can be seen that the bus is inactive now for much of the simulation. This is because the input feature maps are read into the on-chip buffer, and the only remaining bus traffic is to fetch the weights. The next section covers the synthesis and RTL verification of our accelerator. The design is constrained in Catapult to target a 45 nanometer sample library that ships with the Catapult HLS tool. In Catapult design mapping, it shows that the SystemC interconnect memory is mapped to a dual port SRAM. And it also shows that there are two processes, one for reading the data from the memory interface, and the other for performing the convolution, the bias, the activation functions, and max pooling. Both of the processes are constrained to run with a 500 MHz clock frequency. The Catapult architectural constraints GUI shows that the MatchLib connections interface for our design have been synthesized to data-ready valid ports. This can be seen in the interface folder of the Catapult architectural constraints GUI. The arrays folder of the Catapult architectural constraints GUI allows us to map arrays to memories. With this design, the accumulator buffer, the line buffer for the sliding window memory architecture, and the line buffers for the max pooling have all been mapped to dual port memories. Lastly, the architectural constraints GUI presents the loops in the design, and this shows that the KX and KY loops have been selected and are being fully unrolled, which is indicated by the yellow and green icon. This should result in 9 parallel multiplications. After synthesizing the design analysis can be performed using the Catapult Design Analyzer. The Design Analyzer shows how the SystemC plus the design constraints have been synthesized to RTL. Looking at the RTL schematic as well as the type counts in the object view, it can be seen that there are 9 hardware multipliers that have been used to implement this design. This resulted from unrolling the KX and KY loops. Furthermore, the design schematic as well as the schedule view show that the multiplier and add tree has been spread across 3 different clock cycles. This means that Catapult has pipelined the design based on the target clock frequency and the delays of the components. This is one of the reasons why there may be slight differences in latency between the post-HLS simulation, which is simulating the RTL, and the pre-HLS simulation. The pre-HLS simulation does not contain information about the pipeline depths. However, MatchLib does provide a mechanism for back annotating this information onto the pre-HLS simulation. After performing the post-HLS RTL simulation, it was shown that the simulation results are very close to the pre-HLS simulation. The pre-HLS simulation was able to perform a single inference in 0.93 seconds, and the post-HLS simulation performed a single inference in 0.97 seconds. Furthermore, the post-HLS simulation runtime was over 30x longer than the pre-HLS simulation. The pre-HLS simulation took approximately 20 minutes to execute a single inference, and the post-HLS simulation took approximately 630 minutes to execute a single inference. This demonstrates a very powerful feature of MatchLib and being able to simulate the true hardware behavior in the pre-HLS simulation. In this example, we were performing a single inference. However, it would not be practical if we were attempting to simulate multiple frames of video where each frame requires 630 minutes to simulate in RTL. There are a number of other architectural refinement steps that could be done at this point. One would be to increase the bus width to take advantage of more parallelism by reading and writing multiple data in parallel. This would allow us to restructure the code to perform even more loop unrolling for more parallelism, and would also allow us to process multiple input and output feature maps in parallel. The design could also be rewritten to use loop tiling in order to reduce the on-chip buffer requirements. This allows the convolution to be broken up into a number of smaller convolutions in order to reduce the on-chip storage. It does require a change in the code, adding additional looping structures. And then lastly, because the convolution is written as a separate process now, it is very easy to make architectural changes there in order to use something like a PE array architecture to achieve higher performance. The source code examples used for this MatchLib demonstration and other tutorials can be found at hlslibs.org as well as HLSlibs on GitHub. The following case studies show what some customers are doing today with MatchLib. NVIDIA Research built an AI ML inference SoC implemented entirely in SystemC with MatchLib along with Catapult HLS. Their use of MatchLib enabled a full SoC system-level performance verification that was 30x faster than verifying in RTL, with less than a 2.6% difference from the RTL and pre-HLS simulation. They were able to achieve their performance and power metrics with 9.5 TOPS per watt in a 16 nanometer TSMC technology, and their architecture scales all the way up to 128 TOPS. With this design, they were able to demonstrate 10x productivity over a manual RTL design flow, and they went from spec to tape out in 6 months with less than 10 engineers. Another customer, Horizon Robotics, used HLS to shorten their development cycle of a computer vision algorithm for dedicated IP. Their use of high-level synthesis, SystemC, and MatchLib reduced the development cycle from 12 months to 6 months compared to a hand-coded RTL design flow. This included the complete design, the architecture, and all of the verification through RTL coverage closure. They were able to demonstrate that high-level synthesis delivered power, performance, and area equal to a hand-coded RTL design flow, and they found that there were advantages by being able to work at a higher level of abstraction, which reduces the amount of code that needed to be written, as well as they were able to take advantage of some of the HLS C++ IP available. And lastly, there were a number of advantages for performing verification, the biggest being able to compare a C reference model against the synthesizable SystemC MatchLib hardware model. And they found that verifying at the SystemC level can solve many of the functional verification problems. Lastly, the final RTL verification was able to reuse the test stimulus from the SystemC verification. In summary, increasing AI ML algorithm complexity is making RTL verification more difficult. MatchLib and SystemC allows designers to model and verify the true hardware performance, catching bugs early that would normally be exposed during system integration when it's too late. MatchLib models can be directly synthesized to RTL, and the performance of the pre-HLS and post-HLS results are near identical. Customers are using MatchLib today to solve the design challenges associated with building AI and ML hardware. Thank you.